Okay, so you've got this massive project in mind. Could be a chemical plant, could be anything big, really. The blueprint looks great, but uh, how do you figure out the actual cost? Before you even, break ground, that monumental question, figuring out the capital expenditure, the CAPEX, especially when there's so much uncertainty, that's what we're diving deep into today.
Yeah, it's really more than just adding up price tags, isn't it? It's a strategic art form, making these big calls with, frankly, incomplete information.
Exactly. And our mission here is to give you, our listeners, the kind of tools and I guess the mindset that chemical engineers use to estimate CapEx quickly and accurately, even when they don't have all the pieces.
Right. How do you know what really matters? How do you avoid the common traps? And crucially, how do you use the data you do have?
We'll be pulling from some great sources, a guide on CapEx estimation, real examples from NREL reports, on ethanol plants, some data from companies like Braskem, and practical tips from engineering mainstays like Turton's book.
It's really about equipping you with a framework to tackle these seemingly impossible cost predictions. It's about seeing the patterns, applying the methods, even when things look a bit fuzzy.
Okay, let's get into it. Faced with this huge project, where do you even start estimating the cost? Our sources seem to boil it down to three, golden rules.
That's right. And these lessons really guide engineers to prioritize, to work smart in those critical early stages. The first one, and maybe the most surprising, is focus on the main equipment.
Okay, this is where it gets really interesting for me because, my instinct would be you have to count every single nut and bolt.
Yeah.
But you're saying maybe not.
Pretty much. Consider an example from NREL, an ethanol plant using corn stover. Their model had, I think, 133 pieces of equipment.
Wow, 133. Okay.
If you estimate the cost for all of them, the total investment comes out to around $232 million. That's a lot of work.
Yeah, sounds exhausting. So what's the alternative?
Well, here's the kicker. If you focus only on the big-ticket items, the 15 pieces that individually cost more than, say, $2.5 million.
Just 15 out of 133.
Just 15. The estimated investment, $198 million.
Hold on. So you cut down the number of items to estimate by almost 90%.
89% reduction in items, yeah.
And the total CapEx only changed by 15%, about $34 million difference.
Exactly. That's the power of this rule. It drastically speeds things up without a massive hit to accuracy, especially early on. You get, let's say, 85% of the answer for maybe 10% of the effort. It's huge for making quick initial calls.
That is a game changer. Okay, so rule one, focus on the big stuff. What's the next hurdle? My next thought would be, okay, for these 15 big items, let's get exact quotes from suppliers right away. Is that the right move?
That's a very common trap. Lesson 2 is basically resist the urge to over-detail early on.
Why is that a trap? Seems like getting accurate prices is good.
It is good eventually. But getting a formal supplier quote requires a really detailed equipment design. You need engineers spending serious time on specs, drawings, materials.
Right, time and money.
Exactly. And in those early phases, when you might be comparing, say, 3 different process options, just don't have the resources or, frankly, the need for that level of pinpoint accuracy yet.
So the engineer's job at this point isn't to get the final price, but to get a good estimate.
Precisely. You need rapid, sufficiently accurate estimates to compare apples to apples and make those initial go-no-go decisions. Going too deep too soon can actually slow you down or even kill promising options unnecessarily.
Okay, so don't get bogged down in detail too early, which leads perfectly to rule 3, I imagine. If you're not getting quotes, how do you estimate reliably?
This is where we embrace the power of data correlation. And it's something you probably do intuitively.
Like how so? Give me an example.
Okay, think about buying a cooktop. Let's say you want a 5-burner one, but the store only lists prices for a 2-burner, maybe are $320, and a 4-burner, say, $541.
Right.
You can kind of see a relationship there, right, between the number of burners and the price.
Yeah.
You can actually correlate that data.
So you could, extrapolate to guess the 5-burner price.
Exactly. Using a simple correlation method, you might estimate that 5-burner at, say, are $652. And if the actual price tag turns out to be $865.
Wow, that's only 2% off. That's pretty close.
It really is. And the key takeaway, this same principle works for massive industrial equipment. You correlate the price with key parameters, maybe area for a heat exchanger, power for a pump.
Using data from...
Where? From previous projects, published reports like NRELs, or even general engineering correlations found in textbooks, it's about leveraging existing knowledge to make a smart estimate.
Okay, those three rules focus on main gear, don't over detail early, use correlations, that's a solid foundation. But you mentioned different kinds of estimates. It's not all the same level of accuracy, right?
Absolutely not. And understanding this spectrum is critical. It links directly back to the project phase and, well, how much effort you're putting into the estimate.
Like building a house again. Early on, you might just Google cost to build a house. Takes minutes, costs nothing, gives you a huge range. Maybe our $300 to $500 for one type, or 100K to run $300 for another.
Right, a very rough ballpark. But then, if you decide to actually build, you hire architects, engineers. You invest time and money to get detailed plans and much, much more accurate costs. Reduces your risk down the road.
So industrial projects have a similar scale of estimate precision.
Exactly. The guide we're drawing from outlines 5 classes. They range from least precise and cheapest to get to most precise and most resource intensive.
Let's walk through them quickly. What's the roughest?
That's class 5, the order of magnitude estimate. Think plus or minus 30, 40%, maybe even wider, like negative 25% to plus 40%. It's based on costs from similar past projects, just adjusted for basic scale and inflation. You really only need a simple block flow diagram, a BFD, for this.
Okay, rough but fast. What's next?
Class 4, the study or feasibility estimate. Precision tightens up a bit, maybe negative 20% to plus 30%. This needs more detail, mass, and energy balances, a list of the major equipment with estimated sizes, requires a process flow diagram or PFD.
Getting more specific. Class 3.
Class 3 is preliminary or budget authorization. Precision, maybe negative 15% to plus 25%. Now you need more detailed equipment lists, some preliminary piping and instrumentation info, maybe early P&IDs, and a rough plant layout.
Okay, now we're starting to need real engineering work.
Definitely. Then Class 2, a definitive or project control estimate, tighter still, negative 10% to plus 15%. This includes all equipment, preliminary specs for instruments, electrical, maybe some site work.
And the most precise.
Class 1, the detailed or check estimate. Precision is very tight, maybe negative 5% to plus 10%. This is based on nearly complete engineering. You've got quotes for major equipment, all the detailed drawings, civil, mechanical, electrical, essentially ready for construction.
The big takeaway here seems to be that those early, rougher estimates, Class 5, Class 4, they aren't bad estimates. They're actually incredibly useful for what they are intended for.
Exactly. They're perfectly fine, even invaluable, for comparing different options early on, making quick strategic choices, and saving a ton of time and money before committing significant resources. Use the right tool for the job at hand.
Okay, that makes sense. But let's say you find data, maybe from one of those NREL reports, but it's from 2007 for a plant in the US, and you're building in Brazil in 2024. How do you make that old data relevant? This seems like a key challenge.
It absolutely is. Bridging that gap between historical data and your specific project context, that's where the scaling process comes in. It's about applying correction factors.
So what's the process? Find a reference first, obviously.
Right. Find the best reference you can for a similar plant or piece of equipment. Then you systematically adjust or scale that reference value. You need factors for differences in production scale, time, meaning inflation currency, and location.
Let's make this concrete. Walk us through that ethanol plant example again. We want a Class 5 estimate for a 100 kiloton per year plant in Mato Grosso, Brazil, in Brazilian reais.
Okay. Step 1. Find the reference. We found that NREL report from 2011 detailing a 182 ketone year plant in the U.S. with a $422 million CAPEX back in 2007. That's our starting block.
Got it. Step 2 was correcting for scale, right? And it wasn't just simple proportion.
No, definitely not. We use the rule of 6/10. The formula looks like estimated CAPEX equals reference CAPEX times the ratio of capacities, desired over reference, all raised to the power n.
And n is usually 0.6.
Typically, yes. So $422 million times 100 divided by 182 raised to the 0.6 power. That calculation gave us $295 million.
And the key insight there was the economy of scale thing,
Yeah.
or diseconomy, since ours is smaller.
Exactly. Our smaller plant ends up costing more per unit of capacity, $2.9 than the larger reference plant, $2.32 kilograms. It's nonlinear. You have to use the exponent.
Okay, scale adjusted. Next up, inflation. Bringing that 2007 number forward.
Right. We use a specific index for chemical plants, the Chemical Engineering Plant Cost Index, or CEPCI. We need the index value for 2007, which was 525, and the target year. Let's use 2022 for this example, which was 816.
So you take the $295 million and multiply by the ratio of those indexes, 816 over 525.
Precisely. 295 million times 816, 525 gives us about 459 million in 2022 dollars. Using a relevant index like CEPCI is key here, much better than just general inflation.
Makes sense. Step 4, currency. Need it in Brazilian reais.
Yep. Find the average exchange rate for the target year. For 2022, it was roughly R5.16 per US dollar. So $459 million times 5.16 gives us our $2.4 billion.
Okay, almost there. Last step, location. Adjusting for Brazil versus the US.
Right. This factor accounts for differences in labor costs, materials, regulations, productivity, all that. Our source suggested a factor of 1.08 for Brazil relative to the U.S. Gulf Coast based on EPE data.
So final calculation, our $2.4 billion times 1.08.
Gives us our final Class 5 estimate, our $2.6 billion. And just a quick side note, if you were importing a lot of that equipment, you need to add import duties on top, which could be another 40–50% in Brazil. That's a huge factor.
Wow, okay. For $2.6 billion, that's our estimate.
Yeah.
But how do we know if that's even in the right ballpark? How do you sanity check these numbers?
Good question. You compare it against industry rules of thumb or benchmarks. For chemical plants, a very rough benchmark for CAPEX is often something like $1 to $3 US per kilogram of annual capacity.
Okay, so let's check ours. Our $2.6 billion divide by the exchange rate, 5.16, divide by the capacity, 100 kDenon or 100 million kilogram. What does that give?
Works out to about $5 per kilogram.
$5. That's quite a bit higher than the 1 to 3 range. Is that a bad sign?
Not necessarily. It's definitely a flag to investigate further. But in this specific case, the NREL source itself mentions that this particular biomass to ethanol technology is known to be expensive. It's still relatively new compared to traditional processes.
Ah, context matters.
Hugely. And other companies working on similar tech, like Praj, were reporting costs around $4.08 per kilogram. So our $5 estimate, while high compared to the general benchmark, actually aligns pretty well with data for this specific newer technology. It seems plausible.
That's a great point. And you contrasted it with a Braskem plant for renewable polyethylene.
Yeah, their plant was around $290 million for 200 KT a year. That's $1.45 street kilogram, smack in the middle of that typical $1.03 range. So the benchmark is useful, but you have to apply it intelligently.
Okay, that comprehensive plant estimate makes a lot of sense now. But what if you're not doing a whole plant estimate yet? What if you just need the cost for one specific important piece of equipment, like that heat exchanger example?
Right, that moves us towards maybe a class 4 level for that specific item. And it's really interesting to see how you can use different sources or methods and often arrive at pretty similar numbers, which builds confidence.
So the goal was a 100 square meter carbon steel heat exchanger. What were the methods again?
Method 1 was using an online engineering tool like Matcha.com. It gave a price of $46,300, but that was in 2014 dollars.
So you had to inflate it using CEPCI and convert currency to get to 2022 raise.
Exactly. Inflate using the CEPCI ratio, 816 for 2022, 576 for 2014, and multiply by the exchange rate, 5.16. That landed around $338,000.
Okay. Method 2 used data from another NREL report.
Yeah, a 2011 report listed a similar but smaller 47 millimeters exchanger at $24,080 and $2,007.
So here you needed the rule of 6/10 first to scale up the size.
Correct. Scale from 47 to 100 square meters using N.6. That gave about $37,800 and $2,007. Then inflate that using CPCI, 8K16 for 2022, 525 for 2007, and convert currency. Came out to roughly $304,000.
Getting closer. And method 3 was different again in equation.
Right, an empirical correlation from Turton's textbook. It uses logarithms and specific constants based on the exchanger type and area. That calculation resulted in a price of about $25,300, but that was way back in 2001 CEPCI 397.
So another inflation and currency conversion.
Yep, inflate 856 397 and convert currency by 5.16. That gave about $269,000.
Wow. Okay, so our 338K, our 304K, our 269K, they're all definitely in the same neighborhood, clustering around our $300,000. It's actually pretty reassuring.
It really is. It shows that even with different data sources and methods, you can converge on a reasonably reliable estimate.
But wait, our $300,000 is just the purchase cost of the heat exchanger?
Yeah.
We're not done yet.
Not by a long shot. This is a huge point often missed. You need to account for installation costs.
So you estimate that.
A common way, especially for early estimates, is using something called the Lang factor. It's basically an empirical multiplier applied to the total purchased equipment cost,
A multiplier, like how big?
typically between 3 and 5. For plants handling fluids like ours, a factor of 4 is often used as a starting point.
So what does that factor cover? Why so high?
It covers everything else needed to make that equipment operational within the plant. Think electrical hookups, instrumentation, piping connections, the actual labor for assembly and installation, foundations, structures, maybe even allocated costs for engineering, freight, site prep.
So for our $300,000 heat exchanger using a Lang factor of 4.
You multiply our $300,000 by 4. That gives you a total installed cost or total investment module cost of our $1,200,000.
1.2 million. Just for a R300K piece of equipment.
That's right. The installation and supporting infrastructure can cost 3 times as much as the equipment itself. It's often a big surprise for investors who haven't seen these breakdowns before. It highlights that the sticker price is only a fraction of the real cost. There are more detailed methods too, like Turton's equipment module approach, but the Lang factor gives a quick, powerful sense of it.
That's definitely something to keep in mind. Okay, let's circle back to that rule of 6/10. We used 0.6 as the exponent in. How fixed is that 0.6 value? Can we get more precise?
Great question. Yes, we absolutely can refine it. While 0.6 is a decent general default for many types of equipment, especially for Class 5 estimates, specific equipment types often have different scaling behaviors. Using a more accurate hand can improve your estimate significantly.
Like the pump example you mentioned.
Exactly. Let's say we want to estimate a 20 horsepower pump cost, knowing the price of a 10 horsepower pump. The NRAL source we looked at actually recommends using an N value of 0.8 specifically for pumps.
Ah, so not 0.6 for pumps. Interesting. Does it list others?
Yeah, the references often have tables like maybe 0.5 for an agitator, 0.6 for compressor, 0.7 for heat exchangers or pressure vessels. These come from analyzing historical cost data for specific equipment types.
Okay, so using N1.8 for the pump. If the 10 HP pump was, say, $10,250.
Then the estimated 20 HP pump cost would be $10,250 times 20 divided by 10 raised to the power of 0.8. That calculation gives about $17,840.
And how close was that to the real price?
The actual price was $18,530. So the error using N0.8 was only 4%. Really quite good.
What if you had used the generic 0.6?
If you use N0.6, the estimate would have been lower and the error would have jumped to about 16%. Still maybe acceptable for a very early estimate, but clearly using the equipment-specific exponent gave a much better result.
That's compelling. And you also mentioned finding in yourself for centrifuges. How did that work?
Right. If you have cost data for several different sizes of the same type of equipment, say centrifuges with different numbers of frames, which relates to capacity, you can actually calculate the specific N for that equipment line. You plot the logarithm of the price against the logarithm of the capacity, like number of frames. If the relationship follows the power law, you should get something close to a straight line. The slope of that line is your N value.
Clever. And for the centrifuges in the source?
The calculated N turned out to be approximately 0.5.
So even lower than 0.6, what does an N0.5 tell you?
It indicates an even stronger economy of scale than usual. With N0.5, if you double the size, the price only increases by a factor of 2 to the power of 0.5, which is about 1.41 times. If N was 0.6, doubling the size increases the price 1.52 times, 20.6. So knowing that N at 0.5 for these centrifuges is really valuable information for deciding how large a unit to buy you get more bang for your buck by going bigger.
That's fascinating. Okay, so we've gone through identifying key equipment, estimating methods, different classes, scaling, installation costs, even refining the scaling exponent. We have our numbers. Now, how do we present them effectively? It seems like how you show the results is almost as important as getting them.
It absolutely is. You bridge the gap here from pure analysis to actual decision-making. Clear communication is paramount.
What's the first tip?
It sounds simple.
Yeah.
But round your numbers. Avoid showing excessive, meaningless precision.
Like, don't report our $123,345,034.23.
Exactly. Call it our $123 million, or maybe even our $120 million, depending on the estimate's class and uncertainty. Showing all those digits implies a level of accuracy that just isn't there in an estimate, especially an early one.
Right, it creates false precision.
It does, and rounding implicitly acknowledges the inherent uncertainty. It also prevents headaches later if costs shift slightly. You weren't claiming pinpoint accuracy to begin with. Plus, frankly, rounded numbers are just much cleaner and easier to read in tables and reports.
Good point. What else for presentation?
Visualize cost components with graphs. Don't just show the final number. Show how it breaks down.
Like pie charts or bar charts.
Pie charts, donut charts, waterfall charts, anything that clearly shows the relative contribution of different areas to the total cost. For that ethanol plant, for instance, a chart would quickly show that, say, indirect costs are huge, maybe 45%, maybe cogeneration, 16%, and wastewater treatment, 12%, are the next biggest chunks.
And why is seeing that breakdown so important?
Two main reasons. First, it immediately tells you where the biggest cost drivers are. If indirect costs are 45%, you know that refining that part of the estimate will have the biggest impact on the overall accuracy in later stages. Second, especially in an R&D context, it points directly to where innovation could have the biggest payoff. If wastewater treatment is 12% of your CAPEX, maybe developing a cheaper treatment technology is a high-priority research goal. It guides strategy.
That makes perfect sense. Focus your efforts where they matter most.
Well, this has been a fantastic deep dive. We've really unpacked the strategic thinking behind CAPEX estimation. We learned about focusing on the big-ticket items first.
Resisting that urge to get bogged down in excessive detail too early. And the power of using data correlations to make smart estimates.
We explored the whole spectrum of estimate classes, from order of magnitude right through to detailed construction estimates, and crucially, how to scale historical data using those factors for capacity, inflation, currency, and location.
Plus, remembering those often huge installation costs via things like the Lang factor, and even fine-tuning the scaling exponents like the rule of 6/10.
And finally, presenting those numbers clearly, rounding appropriately, and visualizing the cost breakdowns to really drive insight and action.
These aren't just calculations on a spreadsheet. They're really the tools that let engineers, project managers, investors make those critical, agile decisions that, build industries and fuel innovation.
So the takeaway for you, the listener, try to approach any significant investment decision, big or small, with a bit of this engineer's mindset. Recognize that estimates are tools for thinking, for comparing, for managing risk.
So here's a final thought to leave you with. The next time you read a news headline about some company investing hundreds of millions or even billions in a new plant, just take a moment. Consider all those layers of estimation, the scaling, the uncertainty analysis, the strategic decisions based on those early numbers, all happening long, long before anyone digs a hole in the ground. How might understanding that hidden process change how you look at those big projects, or perhaps even how you approach your own major financial decisions?